Okay, so now I want to start again. So let's look at our problem a little more closely. We know we have the momentum principle. We know that that's a differential equation. It's a mass times the second derivative of the position as a function of time over dt squared. And this is minus k sub s x as a function of time. Now, we guessed fairly accurately, in fact, that my equation had to involve something like a cosine of time. And I've left some blanks here because there are important things we need to really pick out to make sure that we're being accurate with our mathematics at this point. Now, a cosine function doesn't just live by itself. It has things within it that we must define, constants that are important. The first constant is the amplitude of the cosine function. And that's a physical quantity that we can look at. If we imagine that our position is going to oscillate back and forth a lot like a cosine function would, if time was running this way and I left this like one of those pens that writes as the paper goes under it, if I put it on a spring like this, it would start, but then as soon as the paper started to go, it would map out something like this. So it's going to look like a cosine function if time is moving this way. So back and forth with a time strip of tape running this way, it would mark out a cosine function. Now, let's think about what we have to define. We have to talk about how far we extend our spring. That comes into a variable here we'll call the amplitude. How tall our cosine function is determined by how far we stretch our spring. That would be something like the original or the initial x position. For now, I'm going to call it A. I'm going to switch to x sub 0 when we change. This is just a generic form. Now, inside of the argument of a cosine, this has to be a dimensionless quantity. It has to have no dimensions. I can't have something that has weird dimensions in my cosine. So what I do is I multiply it by a frequency. It's how rapidly we go back and forth. And so that determines the period, if you will, the length of time it takes me to return back to my original position. So a cosine function goes out, it goes in, and then it goes back. The time that it takes to do that is set by this thing called omega. And you can imagine that that has something to do with the spring. The tightness of the spring will determine how quickly it goes back to its original position. So that's what omega is. It is the frequency of the oscillation of my spring. So how much it goes, how fast it goes back and forth. Surprisingly, it's going to have to involve the mass and the spring constant, and we'll see that in a moment. Okay, so let's just work out our differential equation. Assuming that this is the form that our x position as a function of time takes, let's just plug it in. Let's take two derivatives of it. Two derivatives, we've done this, dx of t dt, well, that's just equal to a times omega sine omega t with a minus sign, and d2 x of t is equal to, dt squared is equal to minus a omega squared cosine omega t. Okay? So here's our position, and here's our second derivative of the position. So now let's plug it all into our equation. We literally take this and chuck it in here, and we literally take this and we chuck it in here. So we get the following. Okay, here we go. Mass times this minus a omega squared cosine omega t equals minus k sub s a cosine omega t. Pretty cool. Now, what have we done? Well, if we look very closely at this, we have terms that are the same on both sides of our equation. Okay? There's that. We have an a here. That goes away. I have an omega squared. There's no balance for that. I have a minus, so the minuses go away. I have an m and a k, so let's just set omega squared equals k sub s over m, such that omega is equal to the square root ks over m. Ha! We have just figured out something mathematically quite amazing. I said this was the frequency. It was how long it took to go back and forth. That's the frequency of the oscillation of my spring. It's the time, in a sense. How long it takes. It tells me about the time. It has units of 1 over time. So the units of this are 1 over time. Now, let's look at it. So if I take, for example, omega, 1 over omega is called something special. It's called the period. Period of the oscillation. It's how long it takes for my mass to go from here to here and back to here. So if it's moving on a cosine function, it would be how long it takes to go from its maximum position through a minimum and back to its maximum. So this is the amount of time that it takes to do this. That's going to be the period. So let's think about what the period looks like. The period looks like 1 over this. It's a square root of m divided by k. So let's think about that physically. If my mass is large, for a fixed spring, if I had put a big mass on there, well, the bigger the mass, the longer it's going to take. It's going to pull back. It's going to go, right? Big mass takes a long time, right? What about the spring? Well, if I have a big stiff spring for a fixed mass, big spring means short time. So it's going to go, it's going to ring, it's going to go back and forth really fast. The softer the spring, the longer the time. Small values down here make these values large. And so we can now start to think physically about our mathematical equation that gave us this lovely solution that helps us figure out omega. The thing that we're missing here in our initial expression is the amplitude. Well, like I said before, this is going to be something like x0. It's the initial position. It's where I decide to draw my spring to. So let's rewrite our position as a function of time. Okay, so x as a function of time for our spring mass system is my initial position, where I draw it to, the x0, cosine of, well, it's omega. Omega is 1 over the period. The period is 1 over omega. So I have the square root of k over m, this k sub s, times time. That is how a spring will oscillate as a function of time. Okay. This thing is called a simple harmonic oscillator. Remember, I said the world is made up of springs. Remember this term, SHO, simple harmonic oscillator. It turns out that most things in the world that beat back and forth and back and forth, pendulum, springs, the rhythm of your heart in some sense. It's a simple harmonic oscillator. These are equations that explain to us exactly how to determine mathematically what the physical manifestations of stiff versus soft springs, heavy masses versus light masses, all those sorts of things are going to be given by this type of equation, something that oscillates in time. And it's the simplest one. There's no damping, there's no loss, there's no friction, there's nothing except a moving mass connected to a spring. And that, I think, is quite elegant. Now, there are some terms that we're going to have to define. And we've done that already, but here I'm going to do it very, very explicitly. We have the period, but let's write the frequency. So the frequency, omega, we call that the frequency. It's not just a simple frequency. It is the angular frequency. Because we're dealing with cosines and sines. Usually those help us understand things like angles. And the reason we use a cosine and a sine, and we talk about angles, is because if I think about it, the angle of my cosine or sine function, depending on what I'm looking at, is going to be determined by some angle here, theta. And if I send this around in a circle, it's going to oscillate around the 2 pi, right? So this is 0 and 2 pi. Just like if I watch the position of one of my values, let's take the cosine value. As this thing goes around, my value of my cosine is going to move inward. It's going to go over here, negative, till a maximum. Then it's going to move back again as my dot makes it around the mark. I go back to 0, and now as I get back to 2 pi, I reach back to my maximum again. So if I really think about it, sines and cosines make total sense as things on a unit circle that are going around and around and around. My value of the sine or the cosine is just going to oscillate back and forth as I go from 0 to 2 pi as my angle changes. The value of the cosine oscillates back and forth and back and forth. Same with the sine. It oscillates up and down along this axis, right? So my sine is over here. And as it goes up and down and up and down and up, sine starts at 0 when I'm at 0 or 2 pi. Cosine starts at 1 when I'm on a unit circle. Back and forth and back and forth. And as my position around my circle changes as a function of time, let's say if I start a stopwatch and this goes around, the values of sines and cosines, they go up and down and back and forth, which is exactly what this is doing. Down, up, back and forth. And the period of that oscillation is 2 pi. That's how long it takes to go from here to here. That is, from here, I go around, I get over to here, that's this point, and I go back to here, that's this point. 0 to 2 pi. So, the angular frequency, omega, for a spring is equal to the square root k sub s over m, like we said before. So, the period of my oscillation, t, period of the oscillation is 1 over. It's the amount of time that it takes. It's how long it takes. So t is equal to 1 over omega. Okay. And so that has to be now in terms of real time. So I need a 2 pi. Right? Because the frequency is equal to omega over 2 pi. So I need this in real time, not in radians. Right? This is radians, so I need this to be in time. So this tells me that I need my omega divided by 2 pi to give me things like 1 over time. So this would be the period. So for this, it's going to be 2 pi times square root of m over k. Yes. Don't get confused by the 2 pi's. It only regulates what the frequency looks like in terms of omega. If I take my normal frequency, back and forth, multiply it by 2 pi, I get the angular frequency. F is the normal frequency. Yeah, both have the same units. Okay,